Okay, welcome to week 5 of quantum field theory. We are making progress. We will finish quantizing the Dirac field, and then we're going to talk about the big punchline in some ways of this class, which is interactions. We're going to look at interactions. We're going to look at, basically, we're going to derive the Feynman rules. Which are a wonderful algorithm for computing scattering amplitudes. I think every physics student in America, undergraduate, knows what a Feynman diagram is. I think any physics student remotely interested in physics wonders how to calculate these kinds of things. And hopefully from your reading, it's pretty clear now where each piece is coming from literally. It's coming from a very simple thing, really. It's coming from a basic perturbation series that we write out, just like we do in quantum mechanics, except now that perturbation series is in lambda, or a coupling constant, which hopefully that language resonates with you after your reading. And so we'll do that, and we will write out that perturbation series. We'll have to do some technical finagling. We'll have to move to the interaction picture, so-called, which really all that means is basically saying, okay, I'm going to split my Hamiltonian into a free part and an interaction part. And if I do some finagling, it turns out I can describe everything in the interaction part with free vacuum expectation values. So that's like the language that we're going to start employing, and that helps us do the calculations. Quick note, just a funny story. I got some emails from people that, not in this class or anything, but people who were writing who were writing papers, and they sent me the site. They said we're published on this site. So you all know what arXiv is, ARXIV. That's like the moderated one. People look at it. It's like what we use to disseminate our work. So this site I looked at was called Vixra, arXiv backwards, VIXRA. So just don't go to Vixra. Those of you that are going and researching and reading papers, which you all should be doing now, you should be going on the arXiv quite often and just seeing what other people are doing. Vixra is not good. Anyone can post papers there. In fact, they even copied the format of arXiv. So I just thought I'd put a PSA out there, those of you that might run into this. So it's not, I couldn't find anything good on there, so I don't know. Anyways, does anyone have any questions from last week or about anything before we get started? Okay, I do have reading, so let me put that up there. The reading for this week, so Lancaster-Blundell, 22, Srednicki, 10, 11, 12, and Z. 1.7, 1.8, 2.1, 2.2, 2.3, 2.4. My hunch, I think, we're not going to get to the actual S matrix today. So I think next week we'll do the S matrix and we'll finish our discussion of interactions. So all of this is review reading, all of this up here, just to get you up a notch up with Z and Srednicki, except this chapter in Lancaster-Blundell, that's a really good chapter on functional integrals, which will be the basis for the path integral. So this is a really important chapter to read because this idea of the generating functional will be very important in calculating these time-ordered products. Okay.
For the Z homework, you wrote 2.2 twice. Did you mean to write 2.1 or did you just
yes, good, thank you. 1.
Okay.
2.1. Good. That's all review, and the Z and Srednicki stuff, after you read Lancaster, after you come to this lecture, after you hear Johnson, then the Z and Srednicki stuff should be very easy to follow. But if you go in there straight, might not be very, well, Z will be helpful. There's not too much math, but Srednicki is a little dense, I would say. Okay, great. Okay, so let's finish the quantization of the Dirac field. It really shouldn't be, it's not really a mystery now what we need to do. We need to impose our commutation relations. No, anti-commutation relations for a variety of reasons. We need to write out our mode expansions, and we need to write out our propagator, right? That's sort of like the three big steps we need to do. So let's do it. Let's do it. Let's do it. Okay, great. So again, the Dirac Lagrangian looks like this. Psi bar, I. Do I want to use my slash notation? I'm going to use my slash notation. Minus m psi. Or really, what I'm saying here, getting rid of the slash notation, this is just gamma mu, d mu, minus m psi. Okay, that's just a reminder that that's our Dirac Lagrangian. One can easily derive the Hamiltonian. Okay, from this, the Hamiltonian would be psi bar minus I gamma dot nabla plus m psi. So that's our Hamiltonian, really our Hamiltonian density in that integral, right? So this is just equal to what? This is just d3x curly h, right? So that guy's our Hamiltonian density. And I figure you can derive that just using the formula we've used before. So now we need to impose anti-commutation relations. Why anti-commutation relations? Does anyone want to kind of tell us why, based on what you've read? Why can't I just use a commutator here of the fields? What's the reason? There's sort of a simple reason, and then there's like a long-winded reason. I'm not going to give the long-winded reason. I think Johnson's going to give the long-winded calculational reason after class. I'm going to give you the simple reason. The simple reason is fermions, the antiparticles are different than the particles. That's the simple reason. And so therefore, in every calculation, antiparticles will take the opposite sign. Okay, so you just trust me when I say that's the reason we need an anti-commutation relation. Johnson will work out more of the details as to if you use commutation relations, what the problem would be. But you know, these kinds of things are very important to, as you go through this course, there's going to be a lot of sort of mathematical things we're using. You should always ask yourself, why is he using that particular thing or mnemonic instead of, because it's not always obvious, right? And so these things are important. So yes, we impose anti-commutation relations between the fields. And so we have psi a of x, psi b dagger of y. Okay, and we get our standard anti-commutation relation where we get the Dirac delta function in position space delta AB for our spinor indices. Okay, hopefully that's okay. Okay, so if I want to create some fermions, right? If I want to create some fermions, now I can do the same thing. I can use creation and annihilation operators. It's like the same game. The only difference now is I'm going to need some extra like junk indices, right? One for the spin, right? And so that's really the only difference. Now our states are spin indices, are going to require spin indices. And of course, the normalization is also the same. So if I have some state P, that's like saying, okay, I have this guy and I have a creation annihilation operator, right? That's acting on this. We'll call this spin, that's a dagger S, and we'll call this P on P, right? So now I just have a creation operator acting on the state. The only difference now is it has a spin index. Similarly, if I want to write this guy, which would be like going from some state S to some state P, I would get my standard guy again. I would get 2EP for this inner product, 2 pi cubed, just with our standard Q of t normalization, delta cubed, S minus P. Okay, so this stuff is hopefully really like basic at this stage. It's not really anything too complicated. Sorry, remember I also have spin indices, so I would need this extra like Kronecker delta, just with the spin indices attached to it. Okay, I can even write a charge. So I can write another charge now using the same kinds of formulas. Is everyone okay with all this? Can I erase? No questions? Okay. Okay, I can even write another charge and another current. I'm just going to put them on the board. You should try and compute them on your own based on the formulas we've written down. So the another charge will look something, let me think. Will look something, I mean, it's going to be a combination again of the creation annihilation operators. And it's going to look something like this. Integral d3x, psi dagger of x, psi of x. I just want to make it clear, these psi's are not wave functions, right? We're all okay with that. They're fields. They're not, I just, because sometimes people get confused. D3p over 2 pi cubed, right? What other normalization? 1 over 2 EP. And I'm going to sum over all the spins. And now I just have my creation annihilation operators, AP dagger S, AP S, minus BP dagger S, BPS. Okay, and that gives you your another charge. Is this kind of expression okay? You should try and compute it based on the formulas I've given you and just see if you get the same thing. Now the Dirac propagator, how would we compute the Dirac propagator? Well, what we're really saying is we want to compute this guy, psi b bar. Wait a second, what did I just write? Is that the charge or the mode expansion? Let me think. That looks like I wrote down the mode expansion. Wait. Let me think about what I'm doing here. No, that's the charge. That's the charge. That's the right calculation. Let's not do this. Let me write down the mode expansions first. Okay, so now we have mode expansions. I'm going to erase this. Now recall, we're going to need, remember in scalar field theory, we had a mode expansion for phi, right? And then we had a mode expansion for phi what? We had a mode expansion for phi that was made up of A dagger, B dagger, right? And that was it. That was the mode expansion. Now we're going to need a mode expansion for psi, but we're also going to need a mode expansion for the adjoint spinner, psi bar. Okay, so let's write those down. Really, again, it's not really that difficult. It's just writing down the same kinds of things we've been writing down, except now we're going to attach these spinners. So psi of x equals the integral d3p over 2 pi cubed 1 over 2 bp square root. I bet you guys are getting really annoyed of writing these down. I just want to let you know, in normal convention, I'm going to start doing this too, this normalization. So d3p 2 pi cubed 1 over square root 2 dp. People just write this down as dk tilde. So they just get rid of everything. So I just, or maybe a d4k tilde, it doesn't matter. But it's really the same thing, just because it makes it easier. Okay, sum over the spins, APS, US of P, e to the minus I p dot x. These are the mode expansions. Again, this is the spinner. This is the creation, annihilation operator. Now I have two objects. Hopefully we know what these U's are. They're just spinners. And we're going to have spinors for the antiparticle, i.e. v, right? That's what we use. We just label it as v. That's just convention. Okay. And obviously I need the other one, the other guy. I'm going to write this as a s of p plus b s dagger of p v s p what e to the I p dot x. That's our mode expansion. Hopefully that's clear. You know what? I did this wrong because really this is just nomenclature. This is ASP. This spinner I should write as US of P because this should not have two indices. I don't really know what your two indices would be. Yeah, so I did it. No, I didn't do it right here. This should be BS dagger P. Sorry, this should be VP of S. This should be e to the I P dot X. Right, because this guy really only needs one index. I don't know why you would have two indices on the spinner. That doesn't really make any sense. Okay, any questions? This is just a mode expansion. It looks eerily similar to our mode expansion in scalar field theory, hopefully. Okay, let's write it for the adjoint field. Again, some mode expansion, d3p, 2i cubed, 1 over root 2p, sum over the spins, right? And now basically, I think you guys can pretty much interpret what's going to happen. All of the signs are going to kind of change. Yes. So basically, we have BSP U bar S of P e to the minus I P dot X plus BP S dagger U bar P of S e to the I P dot X. Bam. That bar takes care of everything. Those are the adjoint spinners. And we have our mode expansions. Of course, when we do QED in this mode expansion, we're going to need something that looks like this, epsilon mu nu. We're going to need some polarization vectors for our particles, right? They're going to be doing all kinds of other spinny things. Man, if particles didn't spin, guys, our life would be a little easier. Now, you guys just read about Wick's theorem and all of this stuff. Theoretically, this is all you need to do calculations, right? And like you could, in a free theory, you could literally just plug this in for every field in your matrix element, and you could just chug it out. Trust me, I've done it. We'll get there in a second, but okay, cool. Any questions? Is all of that okay? Is anyone thoroughly confused right now? I hope not. Okay. This is why we do the reading. Otherwise, we'd have to go way slower. So, okay, very good. Okay, so I guess now would be a good time to derive the propagator. Well, not really derive it, just kind of show it to you because it's kind of a nasty calculation. So again, what are we trying to calculate? We're trying to calculate this expectation value, psi of x, psi bar b of y. Okay, and this is going to give us our vacuum expectation value, i.e., it's going to give us our propagator. So we're basically playing the same game that we played with, what am I trying to say? We're playing the same game we played with free field theory, scalar field theory. And so if you just go through the math, you get I this slash del plus m AB. Okay, so you get this little factor up front, and then you get our standard guy, integral d3p over 2 pi cubed 1 over 2 EP square root e to the minus I p dot x. And that's your standard Dirac propagator. Really, this should be x minus 1. And no square root in the propagator, sorry. Hopefully you've seen that, the Dirac propagator in your reading. You should be going, this is not really the Feynman form. It is not. We're going to put it in the Feynman form in a second. Feynman form is the form we'll use, just like we did last time with that plus I epsilon kind of stuff. And turns out if you work out everything, the Feynman propagator in fermion space, I use an S, is what? Is the integral. Now I write d4p over 2 pi to the 4th. And this will probably be the version you're familiar with in your book. I p minus m over p squared minus m squared plus I epsilon e to the minus I p dot x. Minus y. Okay, this is the Feynman propagator. This is probably what you're familiar with in the book, right? Okay, good. Again, I'm not going to write it down. We could go through the same argument. You have a retarded propagator. You have an advanced propagator, right? I could bring up all of the step functions again, right? These x0 minus y0, right? And so the retarded propagator is when x0 is greater than y0, right? Because then we're going in the forward time. The advanced propagator is when x0 is less than y0, right? So we have two kinds of propagators here. So all of the arguments we made for free field theory apply here. Okay, so I can write out all of those expressions again. I don't think it will be very illuminating because we've seen them exactly in the same form. I would literally just be changing the letter from D to S. Okay, and again, I can write this in a time-ordered fashion. So what I'm really saying we computed is this, just with the time ordering symbol. Okay, does anyone have any questions? Is this all okay? Kind of rapid fire? Because it's really not all that different. Sort of the difficult parts of spin 1/2, quote unquote, we did last week. Like, what is a spinner? Right? Really, like if you think about it geometrically, spinner is really like transforming in this really weird way. It's almost like a spinner transforms in this like weird curly way. I don't know if you can visualize it in your head, but like the proper way to say it is a spinner has like 720 degrees of motion, right? It has two spin indices this way, then it has polarization indices. It can contort in all of these strange ways, really, in like this abstract geometrical space. Any questions before we go to interactions? Okay, great. So let's move to interactions. Okay. The propagator is extremely important. I just want to emphasize that. That's why there's like a whole 2 chapters on it in that book, because it's really like one of the big pieces to the puzzle. I mean, let's draw a Feynman diagram for a propagator. Okay. I have a propagator, let's just say df of x minus y in free field theory, right? This is the Feynman diagram for that. Right? It's just a particle propagating from point x, going to point y, annihilating itself and creating y at that point. That's it. That's what that should. Now I can translate things into pictures. That's the beauty of Feynman. We don't have to write out anything. We can just write out a little drawing and that's it. So this is the propagator. I've translated it in Feynman language. Okay. Now, really, what is this guy? Again, it's just this vacuum expectation value, phi. Just something like this. Okay. So that's the basic idea. I mean, it is complicated, and you went over the whole deep calculation with Johnson, right? It's not a trivial calculation. Honestly, I would really spend time and go over that calculation. Such an important thing for you guys to be able to do. Because the thing is that although that calculation is very tricky, the intuition should be very simple. Okay, I hope. I don't want the intuition to be masked by all of this math. Okay, let's get to the fun stuff. I think nature is not free. Thank God, because if it was free, nothing would be here. The whole world is formed by interactions. The fact that I can see you on my computer screen is quantum electrodynamics at work, right? It's a bunch of electrons and light and interacting. That's what it is. That's what is going on. And, so some of the questions you guys asked last time were very intuitive. A lot of the questions were, well, how do the fields work with one another, right? Are they sort of stacked on one another? Are they kind of separate from one another? And in a sense, there's always interplay between fields. That's how interactions happen. And mathematically, we've quantified this in our mode expansions and the way we've sort of structured our field algorithm, we can call it. So now the question is, well, what happens when two fields come together or bash into one another? Right now, we've been looking at one field on its own, Dirac field on its own. Now let's see what happens when you put in interactions and when we actually get the story down. Okay. So here's our most standard interacting theory. It's the Lagrangian. 1/2 d mu phi squared minus 1/2 m squared phi squared plus lambda over 4 factorial phi to the 4th. This is the famous, should be a minus, sorry. This is the famous phi to the 4th theory. Okay, we'll dub this phi to the 4th theory. And this is our first model of an interacting theory. You're like, why is there a 4 factorial there? It's a bunch of Wick's theorem stuff that helps you with that, so don't worry. This lambda is something called the coupling. Okay, the coupling is a dimensionless number that tells you about the strength of the interaction. Okay. And this phi to the 4th, well, you could have a phi to the 3rd. That's not a problem. You can have a phi to the 5th. I'll leave you to think about why. Now let's just write down an equation of motion for this guy. So we have our standard d2 plus m2, just solving Euler Lagrange, phi. Now we have to differentiate that last piece. And so if I move it over, I get a minus lambda over 3 factorial phi cubed. Okay, so that's just solving Euler Lagrange. Now you may be saying to yourself, okay, this is kind of a weird equation of motion. The thing you should be telling yourself is you cannot solve this with plane waves. You can't now. There are no plane wave solutions to this guy. And so our free theory mode expansions are not going to work entirely. Now, there are two ways to go about this kind of situation. The first thing is to say, okay, can we solve this guy? This is just a differential equation. And so you can ask yourself, can I solve this exactly? No, you can't. It's very difficult. So really in quantum field theory, all of our solutions are perturbative. What do I mean by that? Really all the solutions we come up with in quantum field theory are from perturbation series expansions, and where we take the first 2 or 3 terms of the approximation and drop the rest. Now we got lucky in a sense that we could do that. It didn't have to work like that. It's not as if in every perturbation series, the first 2 or 3 terms give you the bulk of the solution, but it turns out in quantum field theory to work itself out. So QED is a perturbative theory. The weak interaction is a perturbative, what am I saying? Yes, perturbative theory. Actually, it turns out the strong interaction is non-perturbative. There are many non-perturbative approaches to solving QCD problems, which means you can solve them exactly. That's what I mean. You don't use perturbation theory. However, what that means is you use a lot of computers. Use a lot of computers, and you use a whole different framework. So, okay. So this is our equation of motion. We can't solve it with plane waves. We need to come up with some new mathematical scheme. So just a reminder, our commutator between fields. Again, now we're in scalar field theory again, okay? I just want to say that. Pi x, pi y is equal to I delta cubed minus y. So that's our standard commutator. I'm just reminding you of some facts. And so what are some interacting theories? So this is one. This is what we're going to play around with today and next week with the S matrix. And honestly, Lancaster-Blundell is like absolutely incredible for this discussion. I was thinking of just lecturing out of Lancaster and Blundell for these 2 classes, just because I found it to be so good, so clear, so well written. But I'm not. I'm going to do it my crazy way, and then you can read it. So obviously, our next famous example of an interacting theory is QED. We'll be spending many weeks on QED. This is like the big theory. And the Lagrangian for QED can be written in the following way. It's the Dirac Lagrangian plus the Maxwell Lagrangian plus the interaction term. And so what is that? That's just equal to what? Psi bar I del slash m psi minus 1/4 f mu nu. And then what's our interaction term in QED? Minus e psi bar mu psi a. Okay, so this is our QED Lagrangian. Standard Dirac, standard Maxwell, right? Where again, F mu nu is the field strength tensor. Du mu a mu minus du mu a mu. Oh, sorry. It doesn't even matter. Who cares? Whatever. Okay. And we see this funny interaction term. We'll talk a lot about this when we do QED. But this E is the electric charge strength. So it's the electric field strength. This A is what we call the gauge field. Hopefully you've heard of it before. We'll talk about what all of this kind of stuff means, but I just wanted to show you the some of the other interacting theories we could work with. Okay, another way to write the QED Lagrangian, so LQED, is in this way. Actually, I'll write this up top. Okay, so another way to write down the QED Lagrangian is in this way. Just to make it simpler, but it's not only making it simpler, it's introducing a really particular prescription. And that is psi bar I capital D slash minus m psi minus 1/4 mu squared, where this D is what we call the gauge covariant derivative. Okay, maybe you've heard of the covariant derivative. Sorry, which can be written as d mu, capital D mu, is defined as d mu plus IE A mu of x. So this is what we call, so we're going to see in quantum electrodynamics, the only reason I'm showing you this, we're going to look at this much more in depth, but we're in quantum electrodynamics, we're going to impose gauge invariance, which we've talked about what that means. And so one of the things we do to our Lagrangian to get rid of the extra terms we'll get by imposing gauge symmetry is we attach this covariant derivative. And so you get this extra term with your partial derivative. This extra term will cancel sort of the garbage you get from imposing gauge invariance. Okay, so this is the process. So allowing d mu to go to capital D mu is the process of minimal coupling, which is what we'll do in QED. We impose minimal coupling. Very important thing that we do, mathematical aside. Okay, anyways, what else? What else can we talk about? So we obviously imply gauge invariance. So psi of x goes to psi of x times e to the I alpha of x, right? That's our famous gauge invariance. This should really be on the left. That's our famous dude, right? A physicist's favorite symmetry. That's what I always like to say. And then we have our gauge field go to A mu minus, we're going to have some extra trash, 1 over E d mu alpha of x. So you should immediately recognize that these transformations are local gauge transformations. And they're just local phase rotations in space because of this parameter alpha of x. Okay, so, just talking about some of the machinery of QED. Okay. And we get some equation of motion that looks like this. Right, so this is the Dirac field coupled to some electric field. Where again, we impose minimal coupling. So this is the Euler-Lagrange equation from this Lagrangian for psi, okay? It's just a Dirac equation coupled to an electromagnetic field. Okay, we can also write down an Euler-Lagrange equation for A, the vector potential, right? This is not a real, it is a gauge field, but it's also called the vector potential. Okay, it tells you how the electromagnetic field vectors change, right? And this is encoded in this guy, F mu nu. Right? So if we write down an equation for A nu, we get the following. I write it over here. We get d mu F mu nu, which should look familiar as the Maxwell equation, equals E psi bar, gamma nu psi, equals J, some current that I'll define, E J nu, where I define the new current, know their current, J nu equals psi bar gamma nu psi. Again, we're going to go through this a lot. I just want to show you QED, just the basics. Okay, so this is one interacting theory. So we have scalar field theory, scalar interacting theory. We have QED, where we have some gauge redundancies, and we have covariant derivatives, and we have more machinery that we're going to need to employ. But this is a Maxwell equation. This is telling you how the electromagnetic field is evolving. And this is your charge. It's not really, it looks worse than it really is, I think. Okay, let's talk about another interacting theory, which is a fictitious theory called Yukawa Theory. So Yukawa was a great, great Japanese physicist. I hope you've heard of Yukawa Theory from the reading. And Yukawa theory was really interacting theory of scalar particles. And his hunch was that the strong interaction was described by these theoretical particles called scions and scalar particles. He was obviously wrong, so it turned out to be a theoretical theory. But nonetheless, it's very useful because we can explore interacting theories without putting spin into the picture in kind of a unique way, right? So it's a little simpler at the very beginning. So how do we write down the Lagrangian for Yukawa theory? Well, we write it down in this way. So Lagrangian Yukawa equals our Dirac Lagrangian minus Klein-Gordon minus G psi bar psi phi. Hopefully you've seen this in the book. Plus Klein-Gordon. Again, I hope I never get the question, Kyle, how did you derive that Lagrangian? Again, I didn't. We pull it out of thin air and we construct it based on some symmetries. That's it. That's our only guiding principle. Okay, G is the Yukawa coupling. I hope you've seen this a lot. And G will be used as the coupling in many theories. Okay, so now you're probably going, huh? Okay, this is all kind of nice and it's a little confusing, but I kind of get the gist of it. Hopefully that's what you're saying to yourself. That's okay, fine. And the intuitive student might ask themselves, huh, doesn't that mean, I mean, you're writing down all these Lagrangians and whatever. I mean, the natural question someone could ask is, are there an infinite number of interacting theories? I mean, that's the natural question. And then if you're a theorist and you're trying to figure out the theory that describes the world or the universe, really, this is very confusing because it's like, how do I narrow it down? I can write down 5,000 Lagrangians at my desk right now. And how do I know? What's my guiding principle? It turns out miraculously, and we will spend many, many weeks on this, but miraculously, there are only a finite number of possible theories. In fact, it's very constricting, the number of Lagrangians that could describe the world. And the reason it's so constricting is because we demand that our theories be renormalizable. That's the key word. And we'll spend a whole month on renormalization. It's a very technical aspect of the subject that takes a lot of time to really understand. However, I don't want you to think that we're living in some kind of infinite regime where there are thousands of theories. There really aren't. And in fact, people think constraints are bad. Constraints are wonderful. In fact, you want a theory with a lot of constraints and less free parameters. The less free parameters a theory has, the better it is, in my opinion, in most people's opinion, because it means that there's less things to fool around with. It's making clear predictions, making clear distinctions. So you want mathematical constraints. It's good for your theory. We have very precise mathematical constraints on what these Lagrangians can be. So I just want to say that. Obviously, Okay, so what are we trying to compute? Okay, what is our study of perturbative interactions? Let's begin the journey up the mountain, so to speak. And we'll do this over 2 classes, I think. It's going to take 2 classes. Okay, we're trying to compute, in reality, we're trying to compute correlation functions. Okay, I mean, that's kind of that is the story. That is what we're trying to do. It's nothing really miraculous. So what we're trying to do is compute stuff that looks like this. Now we have omega. I'll tell you what that is. phi of x, phi of y. Okay, this is really what we're trying to compute, stuff that looks like this. Omega just denotes that now we're in the interacting vacuum. Okay, it's not the free vacuum. This is kind of cool. This is what we want to compute. This is just the Feynman propagator, right? I have two fields. There's nothing fancy here, but these are the kinds of things we're trying to compute. Now, theoretically, you could compute this with mode expansions. If you had five phi fields, let's say you had four phi fields, phi x, phi y, phi x, phi y, you just line them up and you just write out the mode expansions, do the integrals. What should you end up at the end of the day? You should end up with a bunch of Feynman propagators, right? Like, let's just say theoretically I had something that looked like this. Phi of x, phi of y, phi of x1 we'll say, phi of x2, phi of x3, phi of x4. Okay, and I plug in all the mode expansions and I compute all the integrals. It's a really easy exercise. You just get a bunch of, so you get a df x1 minus x2 plus a df x1 minus x3 and so on and so forth. You just get a bunch of propagators. And now let me draw the picture representation. That means, okay, you have this Feynman diagram, so x1 to x2, and x3 to x4, you have those two processes happening separately. All right, they're just two things. And then you add all of the higher order diagrams. So here's my great anecdote for today. I was a sophomore in high school, so your age, and I was reading about QFT naively. I didn't really know what I was doing. And I wrote a paper computing this guy. Okay, so I said, I want to compute this guy with all free. No, what I did was I put 5 fields. I had 5 fields. And I wrote down the whole computation. And I'm going to send it to you guys when Johnson's giving his session so you can see how crazy I was. I want you to see from high school. I wrote it up. It looks like garbage. It wasn't even in LaTeX. Whatever. I did the calculation. I multiplied everything out. I turned the crank. And I immediately realized my mistake. So this is how you learn. Very naive mistake. What was the naive mistake I made when I was in high school? Look how many fields I put in here. 4. 2 particles. 5 particles is not possible. Because when you work this guy out, so that's what I learned, which was good. I learned that my setup was wrong. Because what happens is the way your propagators come out, you end up having 1 particle interacting with 2 particles, or not interacting, or these are not interacting. This is free. So you have 1 particle moving and somehow annihilating into 2 different particles because you have an odd number of particles to begin with. So it's not even the way everything's working out like this, right? So now imagine I had another particle. I had 5. I had some x5. How would you draw this picture? You wouldn't be able to draw it in some cohesive, free, even way. So immediately I go, ooh, this is weird. The universe can't do this in a free theory. What? So, you learn like that. You make up a theory. You work it out. It took me like 4 or 5 hours. It took me a whole weekend. I was like, I got to, I had some friends help me. We were working. And it turned out that we figured out that you can only have an even number of particles. So that's good. So do this calculation. Do it. It's not that hard. Just write out all the mode expansions and crank through it. Okay, that's my anecdote for today. Okay, so basically what we're trying to do is we're trying to compute this. Obviously with 2 fields, it's not that exciting, okay? If we have 4 or 5 fields, it's more exciting. Not 5 fields, what am I saying? If we have 4, see, can you believe that? If we have 4 fields, it's more exciting. So let's think about it. What are we going to do? And the approach is pretty, we don't want to write mode expansions. Let's just cut that off the table. We want to do this in a more fancy way. Okay, so what can we do? And we can use perturbation theory. So let's think about what we sort of did in perturbation theory. So we have a Hamiltonian. First thing we do is we split it up into the free part and the interaction part. Okay, that's the first thing we do. So that means in our case, for 5 to the 4th theory, that means we have the Klein-Gordon Hamiltonian plus an integral of the interaction term. That's the first thing. Okay, so this is what we're trying to do. Let me think. Now, we're going to have to, we're going to have to work in a particular kind of domain here that is not really obvious at first glance. Okay, we're going to have to work in a particular picture. So what am I really trying to say here? I'm trying to say here is we should always sit down and we should say, okay, what kinds of things can I work with? What kinds of things do I know how to work with? We know how to work with free stuff very easily. This guy is a little more complicated. So the idea is we write a perturbation series in the hopes of simplifying this. We write that power series really in lambda, and we see what we can do with that. Okay, we're going to massage that. Before we do that, though, we need to move into a different picture of looking at the states and seeing how they evolve, called the interaction picture. Now, I have mixed feelings about the interaction picture. I mean, I don't know. I don't think it's very, very useful to have a very, I should be careful in terms of how I say this. How do I want to do this? Do I want to actually go in depth with the interaction picture? That's the question I should ask myself. So here's the thing. I think it is useful to go through the interaction picture. I think Johnson should go through that more in depth because there's many things, aspects of it that I don't really think are so important. I think the bottom line is if we can get from this step to something called Gelman Low Theorem, we're okay. So I don't know. I think Lancaster and Blundell do talk about Gelman Low Theorem. Do they, or? Okay, let me think then. How should we proceed? Okay, then let's just work it out. I'll just work it out for you. That's fine. So let's just work it out. So what are we trying to do here? Okay, we're going to have to massage the states a little bit. Let me just think about how I want to do this then. Because I want to get you to, or maybe I'll just have you read about it. Let me think. Interesting. I don't know if I want to do it this way or if I want to do it in the other way. Yeah, what I'm going to do is I'm going to write down the expression I want to get to. I was just thinking about the calculation. It's a long calculation. I would say go read the steps because I think it's not going to be so illuminating if I work through that. It's pretty long. So let's just write down the final calculation. So the conceptual gist of it is we have to split this guy up because we don't really know how to talk about each int, okay? So actually it turns out there's a very fancy trick we can use called Gelman Low Theorem, which you can read the paper by Low and Gelman, that allow us to write interaction, these guys, in terms of free vacuum expectation values. So I can actually rewrite this guy in the free vacuum kind of way. So that ends up being very useful. So let's write that down. So I have that law written down here. So I can now write down this guy in the following way. This is going to be much easier. I have omega t 5x So I'm saying that this guy now is equal to some. This will be much more illuminating. We'll see in a second. I'll describe it in a second. It's a fraction, it's over. It's a bit of a long expression, that's why I had it written down, but let's talk about what this guy is. Okay. So what am I saying? I'm pretty sure this is in the book. So I don't know if they call it this. So just, make sure you read this in Lancaster-Blundell. I don't know if it's in this form, but basically, what am I saying? Okay. We're going to take some leaps of faith, quote unquote. First thing I'm saying is I can write down the interacting expectation value in terms of free expectation values. That's really great because now it can simplify my calculation. But you're saying, where does the interaction bit come in? Well, the fields are just the fields from my free part. They're the standard thing. And I have this term e to the minus I dt hi. So somehow I've put the interaction part of the Hamiltonian into this bit. I'm sure you've seen this in Lancaster-Blundell, this guy. This is called Dyson's expansion. This is Dyson's expansion. So Freeman Dyson figured out that he could split up the Hamiltonian, the interaction piece of the Hamiltonian, and put it into this exponential. And so we're going to write this exponential in a power series in lambda, pull out the terms that we need, and solve this correlation function. Okay, don't worry about the denominator yet. Let's focus on the numerator. I'll tell you what happens to the denominator. Okay, let's compute the top piece. Okay, it's going to make sense in a second. But I mean, to get from here to here is a lot of arguments that I don't think are worth pursuing right now. So let's focus on the numerator. How are we doing on time? 10:32. Okay, we have plenty of time. So again, we have 0. We have t. Okay, this is the guy we want to compute, the top bit. Okay, and now the question is, well, what do we do with this? That's the main question. So let's take a 5-minute break. Let's take a breather. And then we're going to crank through this guy. Okay. And yeah, okay, it's 33. We'll be back at 37. I'll be right back. So. Is everyone okay? Not too lost, right? Okay. Man, this Vixra thing was really disappointing. I was really surprised to see that. I couldn't believe it. Are you doing in-person school, Jenna?
My school is starting to, but I'm staying home. Like some people go to school, some people don't.
I would say that's a smart decision. Mansoor, but in the city, everyone's in person, right?
No, you get to choose whether you're in person or not.
Where do you go to school again in the city?
Bronx Science.
Okay, good, right. Man, you go to the same high school Neil Tyson went.
Yeah, people love it.
Really, they love him. I met him a few times. He was all right. It's okay. Pretty soon you guys will be writing papers in another 6 months. And then you'll find that you're even more stuck than you are when you're learning something. That's the way it works. I'm in paper writing mode right now, and I have days that I call chicken scratch days. Chicken scratch days are days where you do a lot of scribbling, but you just end up stuck at the end of the day anyway. I have a lot of chicken scratch days when I'm writing a paper. A lot. Many. I would say 90% of my days are chicken scratch days.
How long does it take to like write a whole paper?
It depends. I mean, I think for theorists, the output is quicker because we're not counting on any experiment. I usually write, on average, it takes me about 2 months. It's not very long. I don't like writing very long papers. I'm not that. Some people do. Some people write 60-page papers and have 3 or 4 collaborate. I usually don't collaborate. It's either with, I obviously did when I was beginning. All my papers were with a professor. But now I really work alone, which is really strange for an undergraduate to say. Most undergraduates don't even write papers, so 99.9%. I think I can safely say I know every other undergraduate writing papers. I know them because there's just not that many. In theory. An experiment in astrophysics, every undergrad. I think in astrophysics, especially astronomy, if you don't have a publication as an undergrad, you won't get into grad school. I mean, they expect it. In high energy theory, there's a lot more slack, we'll put it that way, just because it's so much more kind of archaic. And
I know you've talked about like black holes before and stuff, but like what are some other like applications of like QFT to like astronomy?
oh, astronomy. So QFT has a lot of applications to, moving from astronomy for a second, but condensed matter. A lot of applications to condensed matter, quantum information, and all of these kinds of things. Astronomy is weird, right? Because we don't have any quantum theory of gravity. Stuff, astrophysical phenomena is sort of at a big scale, right? So like if you're an astrophysicist and you're looking at black holes, or you're looking at exoplanets, or you're looking at comets, or you're looking at galaxy formation, you don't care about quantum effects, right? Who cares? I worked with a guy named Jerry Ostreicher, amazing astrophysicist, amazing. He was like my mentor when I first started. And I did a paper on galaxy formation. And he never took quantum mechanics, okay? And this is a guy who worked with Chandrasekhar, the Nobel Prize winning Indian physicist, was his PhD advisor. It's like, he's not a slouch. He's one of the titans in astrophysics, Ostreicher. He never took quantum mechanics, right? So like, I don't know, it's tricky. Now the question is like, from my point of view, I do particle physics. So of course, from my vantage point, I'm trying to put quantum field theory into the story in describing gravity. But you know, in terms of 99% of astrophysical phenomena, it's not important. It's just not. So yeah, it sort of depends on what perspective you're starting from, right? If you're a particle physicist and you want to study cosmology, well, what's your first intuition? Oh, how can I write a particle theory of dark matter? Right? That's immediately what you say. But if you're a cosmologist, you don't say that. You don't care. So it depends on what your reference point is, right? If you're a relativist, you would focus more on geometrical aspects of problems. See, like, so when I teach general relativity to someone, I tell them right away, I'm not the best person to teach this, right? Because it's not sort of the way I think about physics. I don't think about things geometrically. I think about things in a quantum field theory point of view. So it just depends on where you're coming from, but yeah. Yeah, I wouldn't say there's many direct applications. I wouldn't even call the black hole problem a direct application because we're not going to solve the black hole problem. There's never going to be a clear experiment that will tell us. There are other clear experiments, I think, but not the black hole problem, sadly. Anyways. Okay, let's continue. So now the question is, how do I compute this? Right, and moreover, you could be asking yourself the natural question, how do I compute expectation values of multiple time-ordered fields? Okay, that's the question. Wick's theorem is going to come to the rescue, right, with this kind of thing, because there's many combinations of the way the fields can mess around with one another. Before we do that, I'd like to define this operation called normal ordering. So let's say I have a string of creation annihilation operators, A, P, A dagger P, A, P. Normal ordering means I put all of my creation operators to the left and all of my annihilation operators to the right. That's just an operation I want to define. I think Jenna brought it up pretty early on. It is not the same as time ordering, right? As you know now, you need that little Wick contracted term, which we'll add. Okay, so for this exercise, let's say I have some interaction Hamiltonian. These are all I's, right? Because now we're working in the interaction space. That's all. That's the only reason I'm using the I's. Okay, and I'm going to split up my interaction Hamiltonian into two, what am I saying? Interaction field, not Hamiltonian, sorry. I'm going to split up my interaction field into two pieces. We'll call it phi I plus of x and phi I minus of x. Okay, so I'm just doing this as a mathematical thing to simplify what I'm about to show you. Okay, where I define the positive modes in this way, phi I plus of x is the integral of d3p. I'm just going to write dk now because I'm tired of writing all that. dk tilde, hopefully that's clear. That's just our standard normalization. AP e to the minus I p dot x. And where I put the negative energy modes in this, in the Hermitian conjugate, AP dagger p dot x. Right, and so now if this acts on the vacuum, it creates a particle. If this acts on the vacuum, it destroys a particle. I'm just coming up with some nomenclature here. Right, and so now let's consider, can I erase these two expressions? Are we okay with this? I'm just splitting up the mode expansion. That's all I'm doing. Okay, so now in this nomenclature, let's consider something where x0 is greater than y0. And let's consider the time-ordered product of phi I of x phi I of y. Okay, how would I write out all the combinations of phi I of x and phi I of y? Okay, and obviously there are now two modes for each field, right? Because I have phi plus and phi minus, right? And there are two fields. So there are four combinations, right? Of the two different modes and the two different fields. So this is just basic combinatorics. And so what do I get? I get phi plus, let me just think about, yes, phi plus of x, phi I. Can I drop the i's? Can we make it implicit that we're in the interaction picture? So it's just simpler. So I have phi plus of x, I'm just dropping the i's, phi plus of y, plus phi minus of x, phi plus of y, plus again, phi minus of x, phi plus of y, plus phi minus of x, phi minus of y. Okay, that gives me this time-ordered product. Notice how the pluses are always to the right of the minuses, right? We have to be careful because we've defined the plus modes as being the modes with our annihilation operators. Okay, so therefore we need to make sure that our plus modes are on the right. Is that okay? What I just did? Okay, I didn't do anything fancy. And now what we can do is we can create an algorithm. We can create an algorithm. Oh, sorry. I think this needs a commutator. Hold on. Yeah. Wait, let me think about this. Phi x, phi minus y. Let me think about what's going on here. Yeah, it's fine. It needs this little term. You'll see why. Actually, no. Sorry, I was thinking about something else. Anyways, now we can come up with an algorithm that will allow us to get all the combinatorics down. Because now, with two fields, it's pretty simple. What if you have three fields or four fields? Then you're getting, you don't want to write all this down. So that's where the idea of the Wick contraction comes in. I hope that should be really familiar because that's really important. And where we're going to use Wick's theorem, okay, to sort of simplify. Because remember, if you remember the Gelman Low Theorem, which I showed you, the numerator had a 0, then it had some time-ordered fields, and then it had this exp to the I integral of the Hamiltonian, right? This was the numerator in Gelman Low Theorem, right? I'm not worried about this right now. We'll talk about this in a second. I'm looking at how to deal with the fields first, how to write out the product of the fields, okay? So we're breaking down that guy. Also, you should read Gelman and Low's original paper. You'll understand it, actually. I'll actually put it in the chat while you guys are working. I have it saved. Reading the original papers of quantum field theory is awesome. It's so cool to see these guys discovering it and writing it down, and you get a lot of cool insight. Okay. So how do I want to write this? Let me think. You know what, guys? Wait. Let me just do this quick. Hold on, let me just do this quick. This goes here. Good. This goes. I don't have that term. This stays. This drops. Minus plus. This drops. I have plus. No, I have another minus. Whatever. One stays. Plus. Minus plus. Plus minus. Okay. Yeah, okay, good. Okay. Okay, I can add the commutator. So that's what I'm going to do, because that's how I'm going to define my Wick contraction. Okay, so this time ordered product, you can add this commutator, which I worked out, it works fine. So you have phi plus of x, phi minus of y. Okay, this is the full time ordered product. Sorry about that. Okay, again, both of these are in the interaction picture. Okay, so now the question is, how do I simplify this? Because I don't sort of want to like write this out because when I have 5 fields. So we're going to define this operation and we're going to call it the contraction, Wick contraction. Okay, that's going to simplify our calculations quite a bit. So we have this operation called the Wick contraction. So let's say I have phi x, phi y. I put a little thing over it, right? Hopefully this looks good. Okay, and it's defined in the following way. The commutator of phi plus of y, phi minus of y, phi plus of x, phi minus of y, for x0 is greater than y0, and the commutator of phi minus of x, phi plus of y, x0 is less than y0. Okay, so I defined it as the commutator. Or actually, I'll do it this way. Apologize. Put a y and I'll put an x. Okay. And so we know, we can immediately say that this guy, 5x, 5y is what? This is just a Feynman propagator. Okay, if I have this combination. Right, because if I'm defining it as the commutator, well, we've derived this, right, in the expectation value to get back the propagator, right? Are we okay with that? Okay. That means now we can define our time ordering operation in the following way. We can define it in a very nice way now. Sorry. So the time ordered product of phi of x and phi of y becomes a really nice thing. It becomes the normal ordered product of phi of x, phi of y, plus now the Wick contraction of phi of x and phi of y. Okay? That just follows from the step we just took before where we wrote this guy out, we had a commutator at the end, and we attach now this term. Are we all okay? Does anyone have questions? This is kind of important, or you'll be kind of lost in what I do. Okay. I hope they gave this in the book. I think they did. They must have. Okay. Beautiful. Okay. So I've redefined then the time ordered product. Now let's see what we can do with this. And we're going to write down a beautiful theorem. I want to end on Wick's theorem. That will put us in a good position for next class. Okay, so now we have this guy written out. And now we have a beautiful idea of Wick's theorem. So now what if I have the time ordered product of 5x1, 5x2, 5xm. How would I write this down? Now this is probably like super daunting, right? Because it's like, oh God, I have this combination, that combination, this. It's actually not so bad now because we have Wick's theorem. And what Wick's theorem allows us to do is it says now that this guy is nothing else but the normal ordered product of phi x1, phi x2, phi xm, plus all other contractions. Okay, that's Wick's theorem. I hope you've seen this, definitely, in the book. Okay, this is super important because it gives us an algorithm for working with time-ordered products. So let's do this for one example, okay? And then we will end class. Okay, so for m equals 2, we just get what we just derived, right? Because we have two fields, and we get what we just derived. That the time-ordered product of two fields is the Wick contraction plus the normal ordered product of the fields. So what about if we have 4 fields? Should we do it? Let's do it. And then we'll end. And then I will give you some final notes. So what if we have the time-ordered product of 5x1 oh gosh, oh no. Time to write a bunch of Wick contractions, right? Okay, so again, it's like the normal ordered product of this, using my Wick's theorem. Okay, plus all other contractions. So how many contractions are we going to have here? We're going to have 16, right? Because we have 4 terms, just the combinatorics. So let's work that out. Phi1, Phi2. So first I contract 1 with 2. Then I do 1 with 3. Remember, these are we'll say it again. Then I do 1 with 4. I already did 2 with 1, so I do 2 with 3. Two with 4. Okay, so I did 2 with 3, I did 2 with 4. Now I do 3 with 4 because 3 went to 2 and 3 went to 1 already. And I think that's it. Yeah, that's everything. I don't know if I missed any contractions, but I think that's it. Okay, now we just use our definition. So the normal ordered product of this guy, for example, if I have Phi2, Phi3, and I take the Wick contraction, sorry, we'll do 3, we'll do 4, and I do the Wick contraction of these two guys, what do I get? I just get this Feynman propagator that looks like that, right? D of f x1 minus x3, right? I just get that propagator. So what I'm really saying is this guy's just a bunch of propagators now, which is what we were speaking about before. So let's write down all the propagators. Man, if only I knew what Wick's theorem was when I did my calculation in high school. I'd be a happy camper, right? Because if I knew Wick's theorem, I would have gotten the propagators right away. I wouldn't have to write out all the mode expansion, work out all the integrals, work out all the math. I would have just said, oh, let me just write down all the contractions, and I get down 10 propagators, and it's wrong because as we described, I have Feynman diagrams that don't necessarily work out. So you see, if my high school teacher, I'm saying it on camera, Mrs. DeLise, if you knew what Wick's theorem was, you could have saved me a cramped hand from doing algebra. Okay, that's all I gotta say. Because this is awesome. This is like super easy now. Now I just have to write down all the contractions and damn, I get propagators. Okay. So let's write down the final answer. So the time-ordered product then for Phi1, Phi2. Sorry, Johnson, I'm going to go a little over.
All good.
Okay, you get D of f. Dot, dot, dot. Keep adding them on. Is this okay, guys? I hope so. Okay, we're making progress. Shall we pictorialize this whole discussion? Let's draw a nice fancy picture and then we'll sign off, okay? Okay, and then I'll wrap up and sum up where we're going. Okay, nothing complicated. Now, you know, we wrote all that down. Now I draw pictures, okay, to tell you what I really wrote out. So I'm going to have 3 Feynman diagrams now. 1 to 2, 3 to 4. That's my first guy. You know what? I'm going to be creative. 1 to 3, 2 to 4. This is technically a perturbation series. Not really, but technically it kind of is. 1 to 4. Yep. I don't know, something like that. 3 to 2. There, boom. So this time-ordered product now, we've written out in terms of propagators. We know that the propagators are free. We have no interaction at all at this point. All we've done is use Wick's theorem to talk about the combinatorics and come up with this algorithm, okay, translating it into picture form. And so we know that computing this string is now just a bunch of Feynman propagators, right? It's the sum of all contractions. We've gotten some kind of perturbation series. And like I said, this is a separate thing. This is a separate thing. They're not interacting. Particle 1 is flying through space. It annihilates itself and gives you particle 2. Well, at the beginning of class, that's exactly what I said you could draw the Feynman propagator as. Okay, so this is the beginning of Feynman diagrams. We're going to have to derive the vertex factor, all of that kind of stuff. That's next time. So next time, where are we going? That's the question. So again, using Gelman Low Theorem, which I'm going to attach the paper while Johnson's giving his thing. Gelman Low Theorem. The numerator in the quotient in Gelman Low Theorem is 0, right? Some time-ordered product. Okay, times exp I integral from some minus t to t dt hi 0. This is the numerator, right? This is how we're going to start computing interactions. We simplified the problem by not only splitting up the Hamiltonian to the free part and the interaction part, we moved to the interaction picture. The interaction picture allows us to write down this kind of thing, i.e. writing down interacting expectation values as vacuum ones. Okay, that's what Gelman Low Theorem allows us to do. We have worked out this bit, right? Oh, sorry, I forgot the time ordering symbol at the beginning. We've worked out this bit, right? This involves Wick's theorem. This gives us free propagators, which is what we should intuitively expect because there's no interactions. Now, next week, we got to work on this bit, the Dyson's expansion. Okay, so this is what Freeman Dyson did. This was his major achievement. He worked out this whole formalism. And this exp to the hi is going to give us some math to work on. And basically, all we have to do is write out this as a power series in powers of lambda. Okay, that's where that language will come in. So we've made step 1. Okay. Okay, very good. So next week we'll look at this term. We'll write out Dyson's expansion. I would read Gelman and Low's paper, which I'll attach. You'll understand it. And we will, then I'll send you Dyson's paper to look at. And then we will write out the S matrix, which is the direct analog of what we did in quantum mechanics, this time for quantum field theory. This should look eerily familiar to what? The Born series, right? We're basically writing out a Born series, just relativistically and with fields. That's it. That's the only difference. Okay, if you have questions about all of this conceptually, mathematically, come tomorrow morning. We can work it out. And now I hand it over to Johnson, who's going to work out some of the Dirac crap. We'll call it Dirac crap with all the indices and stuff. Okay, let me stop recording and I'll hand it over to Johnson.